Assalamu alaikum. In today's lecture, we will cover chapter 4 of your reference book of SCLAR. The chapter title is bandpass modulation and demodulation. So, title title of this chapter is bandpass modulation and demodulation. Demodulation. So, in this chapter, we will cover various kind of modulation technique. For example, BPSK, binary phase shift keying, ASK, amplitude shift keying, PSK, phase shift keying, or FSK. Frequency shift keying, or other like QPSK, quadrature phase shift keying kind of stuff. So these are the modulation scheme that will be used for bandpass modulation. Bandpass means what? There are two kind of signal, right? So bandpass means actually we are not talking about baseband. Baseband signal, we are not talking about that. Baseband signal is actually the lower frequency, the original frequency we want to transmit. Bandpass signal actually the signal which was up converted. Now after up converting, we want to modulate this one so that when we modulate, the signal is up converted, as well as and this facilitates actually to accommodate multiple users. So after modulation, that can be or has to be demodulated. Okay, so every scheme that we will be talking in this, like all these schemes that we'll be talking in this lecture or the follow-up, will also cover their modulation, their optimal decision scheme or rule. So optimal decision rule, as well as uh, probability of bit error or bit error rate, as well as bit error rate. For each scheme, each of these will actually cover this topic: modulation, optimal decision rule, as well as bit error rate. Okay, so our first scheme is BPSK, binary phase shifting. Our first scheme is binary phase shifting. Or BPSK. So in this scheme, the pulse shifting filter or the pulse, because it's a pulse, whenever we are this is a digital modulation, means we are talking about pulse, individual pulse. We're transmitting a digital pulse, so we will be talking about individual pulse. Okay, so the pulse shifting filter or the pulse is given by PT. So BPSK pulse shape. So BPSK pulse or pulse shape is given by PT. So the PT is defined as by T plus 2 pi Fc, where T is this capital T This capital T is the symbol duration. So what is capital T? Capital T is the symbol duration. Now this T is also the integer multiplication of the 1 of Fc. So we can write this T is the integer multiplication of 1 over Fc. So the T can be write as like as K, for example, K of Fc. This K is the integer. This K is the integer. Now we can write it as imagine we write it, or we draw a signal like this. It starts from 0 up to T symbol. Okay, so T is our symbol duration. This T is the symbol duration. This is actually what you see. This is 1 up to 2. So this is there here the value of K equal to 2. So K equal to 2. It's just an example, because K is the integer number. K can be any positive integer value. So we take an example. So K equal to 2. So means this pulse has 2 cycle in this symbol duration. So this contains this signal, this one. This contain 2 cycle. From here to here 1 cycle, and from here to here another cycle. So it contains 2 cycle of waveform or waveform. So what happens actually, this T, it can be written as like this, that T equal to 2 by Fc for this case. T is the, remember, T is the symbol duration. Okay. Now PT pulse PT is normalized to a unit energy. Pulse PT is normalized to unit energy. For K equal to 2, we show that pulse PT is normalized to unit energy. We will show it. Okay. So remember the energy of the pulse E. So we can write capital E. Okay. EP. Okay. EP equal to what? How can we calculate the energy of the pulse? So we use this equation earlier, if you remember, before mid. Let me remember why we use it. Probably let me check. Signal power. Yeah, there is a lecture, probably lecture 4 is the signal power. There we find this one. Energy EP is minus infinity to infinity to the P square E dt, right? So for our case it's 0 to T, this one. So this is the, for our case, this is the duration of T. So 0 to capital T is the duration of the pulse. So 2 by T cos square 2 pi Fc T dt. Right? We actually make it square, P square. Right? So if this is the PT, this is the PT signal, then we can write square of this signal, right? Square of this signal. That's we are actually writing here. Okay. Now, if we solve it, how did it happen? It happens the 2 cos square theta, right? Okay. So we can find this format as 2 cos square theta. You know how to solve it. So 2 cos square theta equal 1 plus cos twice theta. So 1 plus cos 2. So 4 pi fct 1 plus cos twice theta, because there is no 2, so divide it by 2. We consider it extra, that's why, right? So this ep will be what? So if we complete the derivation, then 2 by t into t by 2 plus 1 by t 0 to t cos 4 pi fct dt. This amount will be 0, right? For 0 to t duration. Then we can have 2 into 2, 2, so it's actually 1, which is actually the ep, power occupies energy per bit is 1. Okay, that's actually, we just mean that pt is normalized to unit energy. The energy of pt pulse t is normalized to unity, which is actually shown here. That's actually its derivation. That's how we prove it. Okay, remember our original signal xt. We actually, beginning of this course, we started with this signal, right? Xt is a0 et, right? Remember, where we explain this one, we actually explain this in our signal power xt, right? If I bring those signal, this one is our lecture 4. See, this is actually our lecture 4. Here we actually define xt, this signal xt equal to a0 pt. Okay, if you forget by this time, please go back to our lecture 4. Okay. Okay, now what is this a0? Here a0 belongs to two values, right? It could be either minus a, or it could be either plus a. Yeah, the old story, we did it earlier, where a positive a is representing, because it's binary, so it represents 0, and negative a, it represent 1. In our example, we took an example, a series of data. I forget that stream data. It was 0 1 0 1 1 0 1 1, something like that. Okay, check it. Now here, this a0 contains what? Each a0 carries 1 bit information, right? Either 1 or 0, 1 bit information. We actually covered this concept earlier. Okay, now here we say each bit a0 carries 1 bit information with a, either is 1 or 0, which has a this energy per bit. Okay, so EB is the energy per bit. So this EB is the constant across the scheme, right? It's either 0 or 1, but each bit contains this each bit contains this amount of energy with all the BPSK. So it's a constant across the scheme, across the scheme. Now, what was our information we are trying to transmit? We're trying to transmit two bit, either 0 or 1, right? This is actually our information bit, info bit. This is our information bit. Now, remember, we also seen it earlier that bit 0 occurs with a probability half probability, right? We have seen it earlier. Also 1, it also occurs with probability half. That's why we actually call this as a equal probability. This is a same probability. Now A0, which is actually this one, this A0 or 1 is actually our A0 bit, depending on what its value, right? So it can be either plus, it's either minus of A. A is the could be a fixed voltage, isn't it? Because xt equal to, we know it, xt equal to A0 pt. So what is the average energy? Average energy is nothing but what? Half a square e p when there is a bit 0, for example. This is for bit 0, and also half a square ep when this was for bit 1. Equal probability, right? So this is, but this is actually the average energy is the sum of the energy, like average energy of signal if 0 occurs. 0 occurs. This is also the average bit average energy of signal if 1 occurs. So the average energy is the average energy if 0 occurs plus average energy if the 1 occurs. So what will happen? So nothing but a square EP, which is actually EP is its normalized energy is 1. So it's actually a square. So the average energy is a square. Now, if average energy is a square, then what is its relation with EB? energy per bit. EP is the energy in the pulse. So what is the energy per bit? So A square is E B energy per bit, means A equal to square root of EB. So we find energy for A. So it's a energy per bit. So this gives us actually the average energy per bit, actually, which we actually find here. Average energy per bit. So average energy per bit, that we find. Therefore, what is the transmitted waveforms? So therefore the transmitted waveforms are, if it's 0, then A0 represents plus A, right? Which actually represents EB. What will be the signal then? XT. XT will be square root of XT, actually A0 PT. Remember, XT equal to A0 PT. So A0 is EB into PT. What is the PT? PT was nothing but this pulse was 2 by T cos 2 pi FC T, so that T is greater than 0 with T, right? So we can write square root of twice EB by T cos twice by FCT. So what is this? We find this is actually the waveform. This is the waveform corresponding to bit 0. Waveform corresponding to bit 0. Likewise, this was for 0, and for 1, for bit 1, A0 will be what? Minus A. Same thing we did here, repeating, which will be minus EB. What will be the signal then? XT will be minus EB 2 by T cos 2 by FCT, which is nothing but minus twice EB by T cos twice by FCT, which is the waveform corresponding to waveform corresponding to 1. Corresponding to bit 1. So it was bit 0. So we find both for bit 0 and bit 1 the expression for the waveform, right? So 1 corresponding to bit 0, 1 corresponding to bit 1. If we summarize it, this is for corresponding to 0, it corresponding to waveform 1. Now you will see that this one is nothing but what? We can write it, you see, twice EB by T. We are not using, for example, here we are not using any minus sign. We are not using any minus sign, so we will write it differently. Twice pi FCT plus pi, which will be the same as this previous example. So what is the difference between these two? This signal, when it shifted to pi, you get this signal, isn't it? Yes, it's only shifted by pi. The one signal to another is only shifted by pi. If you add another pi with this signal, then again it will be shifted, right? So if you remember, we uh, we discussed two kind of signal. One is antipodal and another is orthogonal. Antipodals are the in opposite directions, right? If the signals are in the opposite direction, so if you have two signal, then one will be one if their shifting is pi, we got the, so this one, for example, in our case 0 represented here. If we add a pi signal, pi, it will be, so this signal will represent here then by shifting pi, right? If this pi, if you add another pi with this signal, then it will again shift it, it will come here, like shift pi, it will be here. You see, they are antipodal, antipodal. This kind of signal we have seen earlier. So in BPSK, binary phase shifting, there are two state of the waveform, two states. It could be here, it could be here, only they are shifted by pi, right? Okay, so that's why the name comes. So that's how the name comes, that there are two waveform. That because there are two waveform, that's why it's binary. And you have phase shifted, phase shift, phase shift. That's why this two combination give us binary phase shifting, binary phase shift. Okay, this is how the name comes, BPSK. So we shortly call it BPSK scheme. Now, so remember we discussed that. Okay, we will discuss the modulation. We will discuss the modulation. So these topics we cover, that we know what kind of modulation it is, which is BPSK. Once we do modulation, what remains? We do modulation, then we transmit the signal. If we transmit the signal, what is the optimal decision rule? Okay, what is the optimal decision in the receiver? Okay, so let's see what is the optimal decision rule. So, okay, so for optimal decision rule. For optimal decision rule, we'll use, remember, what will give us a optimal, what condition gives us optimal decision. Remember, if we use the matched filter, so optimal optimal decision rule. Of course, optimal decision rule will be when we will be using a match filter at the receiver. We have seen it in previous lecture. The lecture was titled as maximum SNR. When we file maximum signal to noise ratio, then actually we have seen, which is actually lecture 6 in our previous lecture, when we used a meshed filter. Actually, optimal decision rules actually comes when we use this condition. HT, what is HT? Is the impulse response of the meshed filter. HT equal to P T minus tau. That was actually our condition. Now for optimum decision RT, you remember what is the RT? RT is the receive signal at the receiver. So RT is greater than 0, which will decide. Remember what is RT? Okay, let me check. We also, when we talked about signal power, then we receive the RT, right? You see this one we covered in our lecture 4. What is RT? RT is a receive signal which actually received here at the detection at sampling of capital T. You see, sampling at capital T, this RT becomes R capital T with multiplication of the receive signal YT with a convolution of the HT, the response of the mesh filter, which is actually our receive signal. That's how we got a RT, receive signal. So for optimal decision rule, RT, this here T is the sampling interval T. So RT signal will receive as a 0, which will decide what? Decide A0 equal to A, isn't it? If RT is greater than 0 or equal to, which will decide that A0 is A. We are only two digits, right? A corresponds to 0, I mean plus a minus A corresponds to 1 in our cases. Okay, which is actually also equals to the EB, energy per bit. So this is for bit, and this is for bit 0, bit 0. Also RT, if it's less than, which is actually this condition, less than 0, this will decide A0 is minus EB. We just have seen it earlier, right? This one, this two condition. Okay, so this will decide. This will decide bit 1. So this is actually our optimal decision rule. Now, what is the probability of error? So probability. So the probability of error or beta error rate, whatever. So probability of error we already find a generalized expression. If you remember, let me see, probability of error. There is a lecture 7. There, lecture 7, we actually express this expression, probability of error. If I find it here. So in lecture 7, you see, lecture 7, we find the general expression, probability of error is the Q function, square root S square EP n0 by 2. So we can write probability of error is nothing but the Q function. That was our general expression. We already find it, EP by n0 by 2, n0 by 2. Here now we will use this general expression and will apply to our BPSK, binary phase shifting, right? So here A is square root of EB and EP is 1, normalized to unity, right? We just did it earlier. So if we put it for our probability of error, for our case this is general expression. So probability of error, for example, BPSK, our case is BPSK. So the Q function, so S square, S square will be EB. From here, S square will be EB, energy per bit. EP is 1, so this EP is 1, n0 by 2. So n0 by 2, n0 by 2. Okay. So the probability of error for BPSK is expressed by this equation. Of course, we know that the Q function here, off topic, the Q function. You know the Q function. Probably with a probability of error, we actually discuss this Q function somewhere in our lecture 7. Let me check. Yeah, you see, I'm going back to the previous slide. Here, this Q function, we also derive this Q function. Q function is what? A Gaussian Q function. So it denotes the probability that a standard Gaussian random variable is greater than u. So this is the Q function. Okay, we can write it here. What is the Q function? We know Q function, just note here, note that Q function, Q of x, so Q of x is nothing but x to the infinity 1 by twice pi e to the power minus t square by 2 dt. This is the probability that the standard Gaussian with the mean 0 and variance is 1. It's a standard Gaussian with mean 0 and variance 1. So we actually find the probability of error for the BPSK scheme is expressed by this equation, twice EB by 0. See, the reason I have derived this equation, because let me show. Because in your reference book, in the Sklar book, actually these stuffs are not in detail. You see, the first assumption of this equation actually start from here in BPSK phase shifting is twice E by 2. How twice EB by 2 comes, it didn't actually explain. That's why actually I have derived it point by point so that you understand it, how this equation comes. So this is actually more inclusive approach. Here, what we did, let us go back. Okay, at the first side. So we actually completed modulation, we completed optimal decision, we also completed the bit error rate. Here, when you see this modulation, this part happens in the transmission up to this modulation. So optimum decision rule and the bit error rate calculation, it happens on the receiver side or the detection or demodulation, whatever you call it. So in our modulation scheme, we did it, and also how the demodulation scheme, that also be done in this expression. Now here there is an assumption. This assumption that this detection is coherent detection. So it can be non-coherent. Okay, so this is the assumption that these detections are the coherent detection of the waveforms, not arbitrary. Okay, so of course in other lectures we also see if what happens if we do non-coherent detection. Okay, so this is the basics part. So we'll finish here, and we will, in the next class, we will see other mechanism, other modulation schemes. Thank you. Assalamu alaikum.